All right, welcome back everybody to Python for Physics. We are on the end of week 6. And as always, we want to hear how you're doing. How's everybody on your end, your side of the world? We love hearing the feedback of what you think about this course, of the job that we're doing. And we'd love to hear from different parts of the world. I think this has been a really beautiful experience being able to talk to many young, inspiring scientists from different parts and being able to provide a service for you. So tell us how you're doing. Just in the comment section, in the comment box, just tell us a little bit about yourself and how you're doing today. So as promised, this is the second half on lectures on rate of change, introduction to calculus, and solving some differential equations. Before I get to this, let me start with the same administrative beginning. We still have some of you that are new to the class, so welcome. To catch you up to the material that we've covered so far, please send us an email to pythonforphysics@odu.edu, and you will get an automatic reply with all these different links. The first one is going to be a link to our website. We have a lot of information about the course there. The second one is going to be a invitation to join a Slack chat with us, the faculty, and the TAs. You have to be 16 years of age or older to use that. This is a link to the live streams that you're in right now. And then you have the links to the different recordings. The first link will take you to all the recordings of the REYES program, under which Python for Physics is one of them. You will see a little tab that takes you to the archive for Python for Physics. These other two links takes you directly to the Python for Physics archive, and then some breakout sessions that we've had. And then finally, we're making all this material, including our code, freely available for you indefinitely. We get this question a lot, asking if we're gonna, after the 8 weeks, if the material is still gonna be available. Yes, the answer is yes. So we're gonna make it available for you. Our goal is for you to learn at your own pace, for you to enjoy programming and have a fun experience. And so if right now you're too busy, which many of you have become increasingly busy in the end of the summer, if you're too busy, you still can go and use this material later on, okay? So this is going to be made available after the fact. This is what our website looks. Go check it out, please, and send us whatever feedback you may have about that. And then also we have a Dropbox folder where you as a student would have administrative rights. So you can edit the material there. You can put your own code to share with us. This is convenient for us to look at what you're doing and see your progress. If you want to have access to this, just send us an email to this same email with the subject line Dropbox access. In fact, if you send us one email, you will get the automatic reply to the previous one. So it's a win-win, okay? Okay, so this is everything that we have for administrative stuff. I figured I would remind you what the outlook is for not just this week, but the next week as well. So today we're going to finish our introduction into calculus and differential equations. Next Tuesday, we're going to take a little detour, and Dr. Aslam, who is one of the TAs in this course, she's going to give us an introduction into quantum mechanics. So if you haven't taken quantum mechanics, I would encourage you to check out her lecture next Tuesday in this video stream. If you have taken quantum mechanics, I would also encourage you to check it out, because quantum mechanics is one of those concepts that if you think you understand it, you probably don't quite understand it. It's one of the things that takes a while to digest and is to understand it. I think we all benefit from hearing different people's insights into it, and so I would still encourage you to hear her take on quantum mechanics. So please do so next Tuesday. And then after that, we're going to start introducing models, in particular those in infectious diseases, given that we are in the middle of a pandemic. And we're going to teach you how to solve the differential equations that describe the simplest infectious disease models. And so You're going to be able to make your own curves and learn concepts about how to flatten the curve and so forth. And so we're going to try to make sense of that starting next Thursday. Okay, so that's everything I wanted to do for introduction. So why don't we do a quick recap of what we learned on Tuesday. So I wanted to motivate the idea of taking derivatives as trying to think of derivatives in calculus as trying to define instantaneous rate of change. And this is really the motivation behind, in part of the motivation behind derivatives in calculus. So I started by introducing first velocity, and I walked you through, in fact, we first started with position, the displacement, and distances, and then we started talking about speed, and then we introduced the concept of velocity. And so velocity is nothing but the change in position divided by the change in time, okay? And so this is the average, the definition of the average velocity for a time period defined by the initial point in time is t1, and the final point in time is t2. So this bar notation on top on this v is telling you the average of that, okay? And this is the same notation that we use in the beginning, in the third week's lecture, when we started introducing averages and distributions. And so if you think about what this is right here, it's nothing more than the rise over run of if you connect these 2 points by a straight line. We can define the instantaneous rate of change, or the instantaneous velocity in this case, by just taking the limit as the separation between the initial time and the final time is taken to 0. And you can conceptually think about what the slope is doing for this particular graph. Mathematically, we can just define this as the change in position divided by the change in time in the limit that the change in time goes to 0. And this limit is defined as the derivative of x with respect to time, okay? And so this d over dt is a derivative acting on the x, which is a function in this case of time. And so that was my introduction. This was the first instance that we saw derivatives, which is this operation acting on x. And then the second place where this appeared was in trying to define an acceleration, which is a change in velocity divided by the change of time. And in particular, we're interested in taking the estimate of calculating the instantaneous definition of the acceleration, which is the limit in which I take this change in velocity divided by the change in time, where I'm taking the change in time, the limit in which I take the change in time to be equal to 0. Okay, and so this is, as you just from the same definition as before of the derivative, you can think of this as a derivative on the velocity with respect to time. Okay, well, as we said, the velocity itself is the derivative on the position with respect to time. And so the acceleration is in fact the second derivative, because you're acting the derivative twice on t, on the position, sorry. So you're taking the derivative of x of t with respect to t twice, okay? And today we're gonna, if this is not absolutely clear to you, we're gonna flesh this out in quite a bit of detail towards the end of the class, or towards the second half of the class. And so to make sense of this, on these limits where we take changes to, we take limit of where we're taking changes to 0, this is all well defined in calculus. I gave you a little bit of overview, a little bit on the historical background of calculus and the role that these two individuals played. And I defined calculus to be, or introduce the fact that calculus it has two different concepts, differential, or two subfields, differential calculus and integral calculus, and they're closely related. And the focus right now is only on differential calculus. And so the main thing that we're interested in is making sense of these limits, where we evaluate the change on some function divided by the change in the independent variable. And as I introduced far back let me go back. At the beginning of the lecture of last week, I introduced some notation for change. We use the Greek letter delta when it acts on x. For example, it just means the change in x. When it acts on a function, it just means a change in that function. So in this case, the initial independent variable value is x1. The final independent variable value is x2. And so the change in x is just x2 minus x1, while the change in the function is equal to f of x2 minus f of x1. And I also introduced a specific set of notation for x1 and x2, where I separated x1 from x by minus a, where a is going to be some infinitesimal distance in the independent variable that we can vary, and so we're going to play with this, and we started doing this last time. And x2, I'm going to define it to be x plus a, and so now the difference in x2 and x1 is equal to 2a. Good, that makes sense. And then the difference in f, which I've specified a notation now where I've defined delta a to have a subscript a, is going to be f evaluated at x plus a minus f evaluated at x minus a. Okay, so this was just a particular choice that turns out to be convenient, and it's a notation that I'm going to be using throughout my numerical prescription for derivatives and differential equations. So in general, what differential calculus is trying to do is define a derivative of a function and define, in particular, this limit. How do we define this limit, where we take the differences of a function away from 2 points that are increasingly close to each other, divided by the limit in which the distance between these 2 points is going to 0, right? So the point is that these two things are going to 0, and so this is either going to be 0, it's going to be either infinite, or it's going to be a finite number. In general, it's going to be some finite number. So the idea is how do we evaluate analytically, and so that's the purpose of calculus. It's trying to, of differential calculus, it focuses largely on this. But numerically, although this might be a little bit challenging, and it's not always easy how to define this limit analytically, numerically it's quite easy. And so I started by introducing a numerical derivative, which what we're going to do is use this definition of the derivative, but we're not going to take a explicitly to 0. We're going to take a, we're going to keep a to be a finite but very small number, and we're going to see the convergence of this derivative in the limit that we take a to 0. And so I defined a numerical prescription for the derivative, which was very, very simple, almost too simple. But the beauty of this definition, this is the first time that we've introduced this, where I define a function in terms of another function. So this definition holds for any f that I choose to use. F is just a generic function. So I can define f outside of this function. I can make f to be an exponential. I can make it be a sine. It could be a more complicated function, as long as it's a function of x. And so having that, this is quite easy. So I'm defining the finite derivative of this function f to be f evaluated at x plus a minus f evaluated at x minus a, all divided by 2 times a. Easy, right? So pretty simple. We introduced this. I think some of you are already starting to define these, and so I would be interested to hear if you've struggled to do this, or if you have any issues, please let us know. And so I gave you a useful table of derivatives, and I encourage you to memorize them if you haven't, but you don't really have to. You can just look them up. And the point is that we're going to try to reproduce, we're going to use these as a way for us to test our code and make sure that we're doing things that make sense, and we have building some confidence before we try to do some more complicated things. And so I made this as a reference. And here I gave you, we went over this last time, I gave you a prescription on how to define the convergence of a derivative. And the point is that I encourage you to, so what I ended up defining as a metric of the convergence is the derivative on the function with respect to, of the derivative with respect to a. So the derivative of the derivative with respect to a, okay? And then I multiply this times 100 just so that we can see it a little clearer. And the first exercises that the second exercise that I introduced was to test the convergence of your derivative function by varying a while fixing a particular value of x, okay? And so I chose a to be varied from 10 to the negative 5 all the way to 0.1 in steps of 10 to the negative 3. This was a choice, okay? And so then the next plots are just plots that I generated using these different input functions. And so we're just testing the convergence. And so what we expected to see are plots like this, where on the top, I'm plotting the derivative on the exponential with respect to x, evaluated at x equals 1, as I said already. And the point is that on the previous plot, on the table that I mentioned earlier, this one, the derivative of e to the x should be equal to x. And I carefully walked through this in last class. So if it's not absolutely clear, I would encourage you to go back. And so here what I'm showing you is a derivative with respect to x as a function of a, and you see that it's some value and then it slowly starts to plateau to some value over here, which coincides with e to the 2. And one thing worth noting is that this line, this dependence on a, is a quadratic. So this has an order a square error. And you can see that it looks like a quadratic rather than a straight line. And this is something that you can explain if you're familiar with Taylor expansions, and we might talk about this later on. But you can explain this by, go back. By the fact that here I'm making an order a squared error when it comes to evaluating the derivative numerically. And so that's consistent with my figure. And so this was the case for an exponential. This is a case for a logarithm, and I get the result that I expected. Again, it looks like the error that I'm making is quadratic. It's very small, right? It's sub% for any finite value of a, but it's still quadratic. Same thing here. It's a quadratic function, and it's plateauing to this desired value. This is for sine, and this is for cosine. And then this polynomial that I explained in last class. Again, the error that I'm making is quadratic. Okay, so this was the first non-trivial test in your code. Hopefully some of you have gotten there. Let me know if you have had any issues. The next thing was to plot not the function as a function of a, but rather pick a very small value of a and then plot your function as well as a derivative on the function with respect to x. And so here, what I'm comparing my numerical solution, which is a tiny little steps in x. So I made really tiny steps, and you can see that this agrees quite nicely with the expected result, which I plotted on top of it using little discrete points. And so, in fact, I'm going to be using this this symbolic representation every single time. What I'll do is that I'll plot in the continuous line a numerical result, and then in the discrete points, I'll plot what I expected the result to be for some discrete points. Okay. So this was for an exponential, and you see that the derivative with respect to x does behave as an exponential, which is the expected result from calculus. So that's quite nice. And this is just supposed to give you some confidence on these ideas. Here I'm taking the derivative with respect to sine, and you see that the derivative looks like a cosine. It's exactly a cosine, which is what you expected. So very nice. And then the derivative with of cosine is actually negative sign as expected, and it looks quite nice. Okay, so that's been my introduction to derivatives. So hopefully that's been useful. And this is, you can basically evaluate the derivative of any large set of functions. You just using this prescription quite simply. So what we're going to do next is, instead of evaluating derivatives as functions, is start introducing methods for solving differential equations. And so we're going to do this in this two simplest classes of differential equations. I'll walk you first to the simplest class, which are first order differential equations, which are going to be what we're going to be using for solving the infectious diseases models. So this would be quite useful for that, and we're going to be able to reproduce figures somewhat like this, okay, simplified figures of this form.
If I can jump in with a question.
Oh yeah, sorry, I should have stopped. Go ahead, Alex.
No,
I was on a roll.
We just have something that needs to be clarified. Luis Ortiz asks, good afternoon, hope you're also doing well. So when we define A, X taken like a kind of center and A the distance from this center?
Is that the question?
Yeah.
Yep, it is. Very good. So let me So let me pull back up the iPad. This is what we walked through last time. So the idea is that I have some function, some generic function. Let me zoom in. Okay. And I'm interested in evaluating this 2 points. So this point and this point, which are defined by, this point has an x coordinate of xf in this case, and then the function is evaluated at that point. Okay. And then on this right here, I have xi, and then I have the function evaluated at xi. Okay. And so the derivative of the function is defined as this, as the limit where the change in the function divided by the change in the independent variable. So it's this is a ratio of this in the limit that the change in the independent variable is going to 0. And I'm trying to be careful saying the independent variable, because sometimes this will be position, sometimes I'll denote this as x, other times I'll denote this as t. It doesn't really matter. It's just I have some function that depends on some independent variable. In this case, I'm denoting it as x, and I'm interested in the limit as that the change in that independent variable goes to 0. And so what I did is that I define xf to be equal to x, which is the center value of the two, and I'm depicting it over here, plus a, and then xi is equal to x minus a. Whoop. And so x is the centered, and then a is the distance from the center to both of them. So this way I go to negative a, and this way I go to a. Does that clarify the question, you think, Alex?
Yep, I think so.
Okay. And so the point is that because I'm defining x of f to be x plus a, that's what appears here, right? Then x of I is equal to x minus a, that's what appears here. And then the change in delta x is the difference between the two, which, in fact, I calculated down here. You see? Delta x is equal to xf minus xi, which is equal to x plus a minus, in the parentheses, x minus a. You see the x's cancel, and then that's equal, the a's add up, which is equal to 2a. And pictorially, this makes sense, right? Because it's delta x is just a vector that points from xi to xf, which is equal to 2a, and it's positive because it's pointing towards the right. Okay, so there's many ways of thinking about this, all of which are consistent, and it's always a question of what is much more, what's more intuitive to you. Okay, any other questions or comments that we should cover before going ahead?
No, you're good to continue.
Okay, awesome. So let me go back. All right, so let's start with some fun stuff. So differential equations. This may sound daunting, and the point of this is trying to make it not daunting. It's quite easy, actually, some of the stuff that we're going to do. And so by the time that you take a differential calculus class, a differential equations class, hopefully you'll be able to code up whatever solutions you obtain, and so you can always test what your analytical result is compared to what your code says. And so this hopefully gives a tool for you to be able to advance faster in your understanding of calculus, as well as whatever other field you want to apply this. So differential equations, what are they? They're just equations that relate one or more functions and the corresponding derivatives. Fairly general. So here's the simplest example of a differential equation. This is, in fact, the first one that we're going to cover. It's quite easy. So it's where I grab a function of x, and I take its derivative, and I set that equal to some function, okay? This is challenging if I don't know what f of x is. Oh, this is a tricky part, right? If I know what f of x is, I can take its derivative and obtain what g of x is. Easy, okay? You already know how to take the derivative of a function, at least numerically, and so you can do that for any function, and that would give you what g of x is. The harder part is if you don't know what f of x is, okay? And you have information about g of x, but you don't have what f of x is, and so solving for f of x from this equation, that's slightly more challenging, and that's what we're going to cover here. So in general, you can have arbitrarily complicated differential equations. Differential equations are remarkably powerful and important in physics. Many examples appear in physics, and one that are mentioned last time is Newton's force law, F equals ma. And if I write a as a second derivative of x with respect to time, then you see that this is indeed a second order differential equation of x, and we're going to solve this as well. So we're going to show you in the second half of the class how to solve this equation. So it's not hopefully too daunting. There's many exciting ones, and so if you're interested in quantum mechanics, the Schrödinger equation is an important one, and so I would encourage you to check out Dr. Aslan's talk on Tuesday to hear a little introduction into quantum mechanics. Okay, so why don't we go ahead and just jump right in? Okay, so we're going to jump right in, and for motivation, the equations that we're going to see for describing the models of infectious diseases are of this kind, okay? So if we can solve this, I promise you, you're going to be able to solve the ones that we're going to consider next week. Okay, so again, we're going to consider the simplest differential equation. And so what we're going to do is we're going to grab the definition of the derivative of f as the change in f divided by the change in x in the limit that the change in x goes to 0. And I'm seeing a bunch of typos. Let me correct these right away. You can see how the sausage is made, which is a terrible expression. Okay, there we go. I think that fixed it. No, of course it did not. Now it did. Good. Okay. So there's a limit as the change goes to 0. And really what I mean by the change is A, right? The change in delta in x going to 0 is equivalent as A going to 0. And in this case, I've introduced already A. And so really what I'm interested in is in the limit that A goes to 0. And in particular, we already defined what this change in f of x with a little A notation. And it's just defined as this, okay? And so what we're going to do, just as before, is we're going to introduce, we're just going to leave, I'm debating on whether I should do this on the iPad, but maybe it's as fine as this. No, let me go to the iPad. So you have a prescription here on how to do this. Let me walk you through it on the iPad. So I have the derivative of x, of f of x, is equal to the limit as a goes to 0 of f of x plus a minus f of x minus a divided by 2a. And this is equal to g of x. Okay? And so what we're going to do is say and the question is, really, what is f of x? Meaning, if g of x is given, then the question is, what is f of x? So if I told you that g of x is an exponential, can you tell me what f of x is? Okay? And we could try to reverse engineer it or guess the answer and check it. But the goal is to have a prescription that gives me exactly what f of x is. Okay? And so I'm gonna assume that if a is small enough, and what does small mean, right? Numerically, what I can do is use multiple a's, right? Whatever prescription I'm going to use, eventually, I can check that my answer converges for multiple a's, right? So this small enough means that eventually I might have to do tests on the convergence of my result. And because we have a little bit of intuition, you can say, well, let A be in the order of 10 to the negative 3 to 10 to the negative 4, and that should be small enough, okay? So there's some intuition for at least simple functions. And so if A is sufficiently small, then we expect that this is approximately equal to the actual derivative. And so instead of evaluating the actual limit as a goes to 0, what I'm going to do is just assume that a is a finite number but sufficiently small, and I'm not going to take the limit until the end. And so I've introduced some error, right? There's going to be some corrections to this, but I expect that those corrections are going to they're going to vanish with a to some power. Okay? And in fact, this is the first time that I've introduced the big O notation. So this is big O notation, which means that a to the, let's say, third power just tells me that the error goes like a to the third power times the coefficient in front that is a independent. Okay? And so if I'm interested, and this is the asymptotic limit as a goes to 0, so a is a small parameter, and so I'm expecting that in the behavior that a goes to 0, the first correction that appears is going to go like this. And what we saw in the figures before in my convergence test of the derivatives is that I was seeing errors that scaled like a quadratic function with some coefficient that I don't know what it is. But all I care about is that since a is a small number, and as long as c is not a huge number, then the error is going to vanish relatively quickly as I take a to 0, okay? And so here, I'm not going to tell you exactly what value the error that I'm making scales like, but all we have to know is that for sufficiently small a, we expect, in fact, we expect this to scale like a squared from the figures, the numerical evidence that we just checked, right? That the derivative, this form of the derivative is pretty close to the actual derivative, and the error was scaling like a squared. Okay, so we can already guess without doing any algebra that this has to be the case, just from empirical numerical evidence. Okay, and so I define these. If this big O is not so clear from my words and what you're seeing here, I wrote it more carefully on the slides later on. Okay, but the beauty of this, right, is that if I assume that a is sufficiently small, I don't care about the error that I'm making, then I've turned a differential equation, which was this equation right here, right, into an algebraic equation. And so now this is easy. So let me just grab it. I'm just going to copy it. Copy. And I'm going to paste it over here. And what I'm going to do is that I'm going to neglect the error at this point, and then we're just going to remember that there's some error in my results. And so what I can do now is that I can multiply both sides by 2a. And so from this equation, I get another equation, which is this. Beautiful, right? And then what this gives me is, if you know the value here, then I can obtain the value here. So it's giving me a mechanism for me to iterate the solution step by step. So I can obtain the solution iteratively, step by step. And so this tells me that that f at x plus a is equal to f x minus a plus 2a times g of x. Okay, so let me rewrite this a little bit different. What I'm going to do is that I'm going to do a shift in the variables, okay, where I'm going to grab x plus a, and I'm going to shift that to what I want to do. I want to shift x minus a to x, okay? And the way you can do this is the following. Let me just define this to be x naught. Let me introduce an intermediate dummy variable, okay? So I'm going to make x minus a equal to x naught. So this tells me that x naught is equal to x plus, this tells me that x is equal to x naught plus a, right? And I'm going to insert this everywhere on top. And so you see that this gives me, I change x to x naught plus a, right? So that gives me x plus 2a. I shift this one plus a, but I have a minus a. So I'm going to leave, it leaves me with f of x minus naught. The 2a doesn't matter. And then I'm shift this one to be at x naught plus a. But of course, here I haven't told you what x is, right? I can make x to be any variable, right? Or x naught to be any variable, right? And so let me just drop the x naughts, because I really could have done this as a dummy variable, right? So let me label it that dummy variable as x naught. Okay? So this now gives me a mechanism to obtain f of x for any value that I want, as long as I know one point in f of x. And so in particular, let me assume that I know the value. Let f equal the value at x equals 0. And so this is going to serve as some initial conditions. And so this is a jargon, right? I have to initiate my function at some value. So if you give me the function at one value, then with this equation above, I can obtain the function at any other value. That's the claim. Okay? And how do I do this? I do this by, if I know this, then I can insert this function over here. I can evaluate this. I can use this function to give me the value. I can just replace x with x0 above. And so then this gives me f of 2a is going to be f at 0 plus a shift, which is defined by this. And remember, all along, we're trying to obtain f if you give me g everywhere. So I know g as a function. And so if I know g as a function, then this gives me f at, and I need to know g as a function everywhere, and then f of f only at one point. And so here I've generated the next point in the list. You can imagine making a list of f at all points in x that I want. This is the next point. Then, having known this, I can then obtain f of 2a, or 4a, sorry, from this equation, from the point at 2a, this way. And so forth, right? So I can evaluate now this at any point, right? So this just becomes, essentially, you can just do this by, you guessed it, a for loop, right? I can just write a for loop that just runs over all the possible points in x and just tabulates all possible values of f from the previous values in f and the g function, and that gives you everything. It gives you f at all the possible values in your in the region that you're interested in. Okay. So that's essentially what I walk you through in these slides. So I start with this definition of the derivative in terms of the finite difference. I keep a to be small but fixed. I do a little bit of algebra to rewrite this equation this way, and I just walked you through that algebra. Then I do that shift in the variable of x naught. So I rewrite the differential equation this way, and then I say, since x naught is a generic name for that variable, I can leave it as x. And so I leave it as this, okay? And then the point is that if you give me a first value of f of x, then I can obtain the other one. So here's a little picture of what's happening. So I'll have f of 0, and then I use this equation to obtain the next point at x of 2a, which is exactly what I just wrote down before. And so I obtain this point. And then, so the point is that this is a given, this is a value you obtain. And then I obtain it for another point, just separated by 2a, and then another point, and so forth. Okay? And so that's it. That would be the solution to this differential equation. Of course, you have to write code to put this in practice, and you can imagine that this is just going to be a simple for loop. And so let me show you my code. So first part, or first thing you need to do in this subset of the lecture, so exercise 4 by my count, is to do the following. First, just write code that solves the differential equation that we wrote down for any given value of g of x. Okay? So any function, I should say, any function of g of x. And so we can use the same trick that we used before, that we can define functions of functions. So that's good, right? So I'm going to write code that holds for any function g of x. And that it obtains f of x for a range of x values, okay? So I'm going to have to give it some range of x values. And so to do this, you can use a for loop that just reiterates the equation obtained in the previous slide, okay? So just this equation that I wrote down before. And so here's my code. You can, as always, I encourage you to write your own code, but I always like to give you mine in case you get stuck. And I just wanted to highlight that this is actually pretty short code. I can write this very small, but as always, I padded this with a lot of comments for you. But you see the lines of code are 1, 2, 3, 4, 5, 6. Pretty short, right? Most of it is comments. So you have here big comments explaining what I'm doing and separate. I'm trying to solve this equation by discretizing it, and then I do a little bit of algebra and I rewrote this in a different way. And then I give you, I want to initialize f, and you see I make a list that includes all the possible values, and I put in the first value, which is an input. So you see the arguments of my function are the input function g of x, the first value of f of x, and then the list of x's. Okay, so there's going to be a list, and you see that here I'm running through that list, but I'm skipping over the first element. Okay, and then a, which is a separation between is half the separation between the first point and the second point, right? And that's it. It's pretty simple. Okay, look, I use some tricks where I grab the previous element of the list. So -1 bracket -1 of a list gives you the previous element, and then I define the change in f in terms of the derivative, in terms of the g function, and I use a little bit of trickery here to rewrite the argument of g of x. So it looks a little bit different than this, but hopefully I explain why that's the case. But you can use whatever makes most sense to you. Okay, so that's my code. What I'll walk you through next is examples of how to test this with some functions that we know the solutions to. Okay, and so they're basically the same functions that we've determined previously. So the first one is an exponential. So g of x here, you see what I'm showing you in these figures is what I want you to reproduce. So put your code to a test. That's this exercise, okay? And so here you see that I'm plotting somewhat similar to before, where on the bottom I'm showing the input function. So this is a function that we know, g of x, and I'm trying to solve this equation for f of x. I've used a very small value of a. I didn't actually have to do the convergence test this time, but you're welcome to. I encourage you to, as always. And then I'm plotting x from 0 to 5. For the input value in these examples, I'm using the initial value is equal to 1. You can't see it in this scale because it's pretty close to 0 in this scale, so you can't see that. But then the green points are what I know to be the solutions. How do I know that is a solution? Well, I did a little bit of reverse engineering. So basically, you can just guess the solution, but let's check that it is indeed the solution. I'll walk you through this exercises, and then I'll take some time to answer whatever questions you might have. So if you have some questions, you can go ahead and put them in right now, and we'll get to them in a second. So the first exercise is essentially solving for f of x, where f of x satisfies this equation. And so how do I know this is a solution? Well, if we go back to my handy dandy, and the point is that I know the solution has to be that f of x is equal to an exponential. Of course, I don't always know the solution, right? This is me putting these ideas to a test. And so how do I know that? I go back to my handy dandy table, which is right here. And I know that the derivative of an exponential is equal to an exponential. And so here I have the derivative of a function is equal to an exponential for all values of x, right? And so that has to be that the function has to be an exponential. And so the other examples that I'm going to use are going to be related to sine and cosine. So let me just write them down, the identities. So the other identity that I'm going to need is that the derivative of x, the derivative of sine of x with respect to x is equal to cosine of x, and then the derivative of cosine of x with respect to x is equal to negative sine of x. Okay? So those are the other identities that we're going to test. And so I'm going to have, so this was the first exercise that I asked you to do. So here's my numerical solution, right? And so you're going to have to write a code similar to this, solve it for a range of going from 0 to 0.5. Was it 0.5 or 5? I think it was 5, actually. 5. From 0 to 5, a set it to 10 to the negative 3, loop over this, right? Output it, and then make a figure, right? So things that you've already learned about, right? So these are things that every single time that you have some output, you're going to have to make a figure, okay? So to visualize it. So that's part of what you've been learning about and reiterating every single time. And so my red is my solution. The green dots is what I expected, okay? And so I use the plot function in matplotlib, and then I use the error bar function in matplotlib to make the green point. So I plotted this with the plot function, this with error bar. And my code that I've used to generate this is already available in the Dropbox. So if you want to take a look, feel free, okay? So I expected an exponential, and look, I definitely get an exponential. Great, that's awesome. So this routine works out. Here I have a different function, which is I'm taking the derivative of f and setting it equal to sine of x. Okay, so let's look at their identities. So if I look back at my identities, you see I need to solve the equation where the derivative of f of x is equal to sine of x, right? All right. And so if I look at these, I see that that's this case, but I'm off by a sign, right? Which means meaning the derivative of cosine is equal to negative sine of x, but the input function is equal to sine of x. So that means that in this case, f has to be equal to negative cosine of x. And that's indeed what I get. So my numerical solution, again, is in red. My input function I plotted here to visualize. My numerical solution is in red. And then the green dots is what I expected. So makes sense. It works out. That's nice. And then the last, you guessed it, is the input function is cosine. Well, let's look at my handy dandy list of identities. Oh, I only have one left, which is this one, right? And you can see that if f of x is equal, the derivative of it is equal to cosine of x, keep writing theta, is equal to cosine of x for every single value of x, that means that f of x has to be equal to sine of x. I was almost writing a theta. And that's indeed what I get. So the numerical solution is my the red, and then for comparison, I've plotted sine of x. I don't have a mechanism just yet, right, to say from my numerical solution, is that a sine function? Is there a cosine function? I haven't really defined a prescription to do that. We can define something like that to test if indeed this is a sine or cosine. But I can compare it to known solutions, what I expected, right? So this is just to test that your code is working and that you're indeed solving the right differential equations and that you're propagating, that your loop function is done correctly and everything else, okay? So I think that's pretty much it. So this routine that hopefully you would have written right here would allow you to solve this differential equation for any input function. So you can use it any single time. Sorry, maybe there's a good time for questions while I figure out how to get my display back on. Oh no.
We have another clarifying question from Luis Ortiz. They ask, so then the reason that a doesn't matter is because in one way or another we were talking about the same function. Is a like a tool for us to be more or less precise?
That's right. Yeah, a is defining the distance between the initial and final point, and is quantifying the error that we're making. And so the smaller a is, the I think it's my laptop that died.
Oh, okay.
Yeah, we'll see. So the smaller a is, then the closer we are to the desired answer. So are there any other questions at this point? Because we might need to take a break. My computer doesn't come back.
No questions.
Okay. Well, why don't we take a couple minute break then? I don't know what's going on with my computer.
I think I might have ran out of battery. A few people were warning you about that.
Oh, why didn't you guys warn me? Warn me.
I think I saw it too late.
Oh my god. You're throwing me under the bus, guys. What's going on? Okay. It's coming back. All right. Let's take a quick break while my computer reboots. Sorry, guys. I thought that I was connecting my computer. There we go. That's almost come back.
It's still not coming through. Oh,
No. I'm good.
okay.
Sorry. All right. I think we're almost back. Sorry, everybody. I got too excited telling you about derivatives. My TAs didn't let me know. Why do we pay you guys the big bucks, huh? Let's see. So no questions. Everybody gets derivatives and differential equations right away.
Well, Raul,
Yes.
you got a question from Brian Go from Medan, Indonesia, asking next week, are we gonna learn about Runge-Kutta or predictor corrector method? He's asking if we're gonna get more advanced methods to solve differential equations.
I wasn't planning on it. In fact, we figured instead of focusing on doing more accurate methods, we would think about more interesting problems. So, no, I think for what we're doing, this is probably going to be good enough. I'm debating about if we'll have time to cover other topics other than the ones that we're going to be introducing next week. There was interest in doing some Fourier transforms. I was thinking about perhaps solving integral equations because that's something I've been doing a lot in my research lately. But I'm not sure. We'll think about it. Okay, I think we're back. So why don't we, on the second half of today's lecture, let me, are we good? Does anybody have any questions? I'm hearing a little bit of feedback. Okay. Let me sort out the iPad again. I think you might get an up-close picture of myself. Okay, so we solved the simplest differential equation. We get a little bold and think about harder differential equations. And this one is going to be particularly interesting for things that we already touched on in physics. And so why would you be interested in a second order differential equation? Well, we talked about the velocity as the rate of change of position with respect to time. And we already brought up that the acceleration is the rate of change of the velocity with respect to time. And velocity being the rate of change of position with respect to time, then the acceleration is the second derivative of position with respect to time. Actually, I think maybe Juan, do you have the speaker on or somebody? Because I'm hearing a little bit of glitching echo. Okay, maybe it's gone away. Okay, so what we're going to do is now try to solve this equation for any given acceleration so that we can obtain position with respect to time. And if you remember back at the first set of lectures that Professor Rogers introduced, he introduced a problem related to projectile motion, and he used these equations where the position with respect to time was equal to the original position plus the velocity, the original velocity, the component along the x direction of the velocity times time plus the x component of the acceleration divided by 2 times time squared. Same thing for the vertical components. And so you can ask yourself where these equations come from, and they come from solving second-order differential equations for both position and for both the x coordinate and the y coordinate in position. They're both related to the acceleration along the x coordinate and the acceleration along the y coordinate. And both of these solutions, come not for any solution of A, but rather when both A's are independent of time. And so they come from solving these equations, not for where there's time dependence and acceleration, but where they're time independent. And so they correspond to the solutions. And so what we're going to do is try to solve a problem like this in general, numerically, and then try to compare it to these solutions and test that indeed these are the right solutions, or at least that they agree with our numerical solutions when the acceleration is time independent, but then we'll see that they don't agree with the solutions when the acceleration is time dependent. Okay, so let's get to it. So the problem that we're going to solve is this one in general. So in general, what we're going to try to do is write second-order differential equations for a function being equal to another function that I'm going to call h of t. Okay? This is perhaps a slightly daunting task at first, but this becomes quite easy if we take a few steps. So first, let me walk you through this. Let's do it on the iPad as well. Again, instead of... So you have the steps. Sorry. There we go. So we have the steps laid out here in some detail, but let me just walk you through them bit by bit on the iPad. So the equation that we want to solve is this one. And now I'm going to use time as the independent variable, of course, because I'm interested in this to the kinematic equations that we considered before. And their time was the independent variable. Okay, so this is the equation I want to solve. And I can write the left-hand side as follows. To make sense of the second derivative, I can just say the second derivative is equal to the derivative acting on the derivative of the function. That's what second derivative means. It just means I act the derivative first, and then I act it again. Okay? And so what I'm going to do is define another function, g of t, that is equal to the derivative of f of t, just like before. And so that tells me, since this is equal to this, right, then this is equal to the derivative with respect to time of g of t. Okay? And why is this useful? Because now, if I insert this above, if I just insert these identities above, then I have that the derivative with respect to time of the derivative with respect to time of f of t, which is equal to the derivative of g of t, is equal to h of t. And so what I've done is that I've grabbed this first equation and then replace them with two equations. Here's one, and here's one. So I've replaced, let me just rewrite these. is equation number 2 here, and equation number 3. And so I've replaced one equation that is second order with two equations that are first order. Why did I do this? Because we already know how to solve first order differential equations. And so if I know how to solve one first order differential equation, then I can probably know how to solve two. Okay? And so that makes things a little bit easier rather than trying to figure out a completely new mechanism for solving this second order differential equation. And so that has allowed me to shift the problem from this now to solving these two. But I know what the solutions are. So I know how to solve these numerically. I'm just going to follow the same steps as before. I'm going to introduce a discrete separation between all points, which is A. And so I'm going to rewrite the derivative as a shift in the change in G divided by, so let me just go back to here, just to stick to writing everything in the same. So let me copy this equations, copy. I'm going to paste them over here so we know what we're looking at. And so I'm going to introduce A. I'm going to set this to be small, but not 0. Okay? And sufficiently small that I'm going to ignore any error that I make with A. Then the derivative of t, well, it's the same as before. The derivative of f, the same as before. And then the derivative of t, the derivative of g is the same as before. And so I know how to solve these, right? I follow the same steps as before. And so let me remind you. So for this one, I multiply both sides by 2a. And then I shift this guy to the right. And then remember, I did a little bit of algebra to shift all the arguments by a factor of a. So what that does is that this becomes 2a. This becomes just t. And this becomes t plus a. So that was the solution to that. And so again, you see, I need to know the original point in t. So t0, that will give me a way to get all the other ones. But the point is that I don't know what g is, right? I don't know what g is just yet. And so I need to, all I know is h. So I'm going to obtain h from equation 3. I'm going to obtain g from equation 3. And so equation 3, you can imagine, which is this one, right? I'm going to do the same steps. Solve for, let me move this up. Well, I'll get the same solution as before. or same form of the equation. And so now you see that I can first generate every single value of g given some initial value in g and some initial value in some function of h, some of h. So if I know h and some initial value in g, I can generate all possible values of g. And then that's going to serve as an input over here to then obtain f from all possible values, for all possible values of t. And so this is exactly what I have in my code. There's one caveat, right, that here you might say, I'm interested in g at t plus a, but I've only obtained g either at t or at t plus 2a. So what I do in my code, you can, in fact, just replace it here. This is the place where I explain. So let me walk you through this. So here, you're interested in g at t plus a, but you've only obtained g at t plus 2a or g and t at t. You can make the meshes for each one different so that you can in fact hit this point directly. But you can also replace let me go to the, you can replace this g at t plus 2a or g of t, and the error that you're making is going to be further suppressed by yet another power of a. What I end up doing is that I replace g of t plus a with the average at a point just above and a point just below. And the error is going to be suppressed by not one power of a, but in fact 2 powers of a. How do you show this? Well, you have to, so here's where I introduce the big O notation, this calligraphic O, and this tells you that the error behaves in the asymptotic limit. It tells you how it behaves in asymptotic limit, which in this case, we're considering the limit as a goes to 0. And proving this approximation that, in fact, this scale is like a to a squared can be done using Taylor expansions. Okay, that's the way that you would show this. And so what I do is that I replace g of t plus a with this average. You can just use one or the other, in fact. And just intuitively, what are we doing? We're doing that if you're thinking about g of t and you're interested at some particular point, and you'll obtain this at t naught plus a, or it's actually 2a. You're interested in this at t plus a, and you've obtained, doesn't really matter, but let's make it nice. At t naught plus a, and t naught plus 2a. So you're interested in the point right here, and you've obtained 2 different points nearby. Then the average is just going to be right at the middle of the 2. It's going to be this point. So it's a good approximation, and it's fairly suppressed. The error that I'm making is fairly suppressed. So that's what I do in my code. Okay. So the point is so in summary, we've replaced a second order differential equation with 2 one-order differential equations. Which we can solve, assuming that we know an initial value of f and an initial value for g, and then we can determine this function everywhere. And so that's it. That's all you need to do. And so I'll show you how I solve this numerically, how I implement these equations numerically. And the goal is to compare them. So in the next exercises, what we're going to do is compare this with the kinematic equations that we used in the lectures by Professor Rogers, which are these equations. And so the first thing you should do, since we're going to compare these equations, is if you haven't written code for these equations, first go ahead and do that. So here's my code for x, the functional form of x, where I give it some time, initial position, initial velocity, and initial acceleration. And we're just going to think about one-dimensional kinematics here. Sufficiently hard, okay? Then the position in x is going to be the initial position plus a shift in x due to velocity and then the shift due to acceleration. The velocity, in fact, we didn't write down. Oh, we did actually. So I think this actually have all the kinematic equations. Very good. There we go. So let's move this. Good. So the velocity is the derivative of x with respect to t, which if you use this handy-dandy table of derivatives for polynomials, you can derive from this straightforwardly. And so the velocity as a function of time is equal to initial velocity plus acceleration times time. Okay, and that's what I did. You give me some velocity if I want to obtain the velocity at t, you give me initial velocity and acceleration, and I can obtain it by this. Is somebody trying to speak? No? We're good? Okay. And so that's, if you haven't written code for that, it's quite simple. So go ahead and do that. It's so simple that I didn't bother to put comments. But in general, we should, right? So the next thing is to write code to solve for f and g, right? Because you're going to generate both given h. And so remember, h is your second order derivative of the function f, and g is the first order derivative of it. And we can do this using the algebraic expressions that we obtain, right? So this gives us a value for any value of t given the initial conditions, right? And so all we have to do is just iteratively obtain every single value, right? Again, here's my code. It looks somewhat daunting, but look, the first part is just a whole lot of comments just to make everything very clear. And in fact, you see BB Edit is even pointing out my typos. So thank you, BB Edit. So what we're trying to solve is this equation. I should have put t, but okay, you get it, but it doesn't matter. It's second derivative of f, so then it equals the function h. And we replace this with two first order differential equations, in which we can solve algebraically using these equations, just basically showing it exactly what I told you. And we're going to put the outputs into this list that I call f of s, g of s, or gs, fs. And we need to give the initial conditions, which are the initial values of these functions at t equals 0. And you see that the arguments of my function is h, which is a function, f of 0, which is a value, is a number, g of 0, which is a number, t of s, which is a list, and a, which is a number, okay? And the last point that I make is this issue about wanting to evaluate t plus a. So I instead of doing anything too smart, what I decided to do is just replace this value with the average of the two nearest values good enough, okay? And so I call that g bar. And so here are my initial values of the list of gs and fs. And then I loop again over t, starting from the first element all the way to the second element all the way to the end. And what I do is that I first solve the equation for G. Why do I do that? The reason that I do that is because F depends on G, right? And so I first need to obtain G, which I can obtain from H. So first I have to obtain G, and then I have to feed that into F, okay? That's the logic. And so I start first by obtaining G, initial condition, initial value, the shift in G, and that gives me the value the new value that I want. Then F, I grab the initial condition, the initial value of F, and then notice here, this is something kind of cute. So I'm interested in the average of the last 2 points in G, right? Remember, I already determined one value, the most recent value, and I fed it into the list of GS. And so here I'm grabbing the value that I just calculated plus, so that's this one, plus the previous one. And then I'm taking the sum of them and dividing it by 2. So that's what I call G bar. And then I just calculate the shift in F from G bar times 2 times A, and then I feed that into my list. And that's it. I'm done. And I just loop this over T, and that does it. Fairly simple. So that's all you have to do. Just try to write similar code. I'm sure you can write smarter than code than me. If you get stuck, we can try to get you there. So try to get you to resolve your issues. Well, what is the last thing going to be? You've written some code to solve not just one, but 2 classes of differential equations, first order, second order. Good for you. Great. How do you know they're right? How do you know that your code is right? Well, put it to a test. Let's put it to a test. So you should always try to test it with things that you know, right? And we know that the solution, so we know what the kinematic equations have to be, assuming that the acceleration is constant, right? So here is what, in general, the velocity, the position has to be as a function of time for a constant acceleration. And so here I've considered 3 simple examples. First one, I give the initial conditions for X and V to be 0 and 1, and I'm using dimensionless units here, okay? So length and time have the same units. Simple. So X is at 0, V is equal to is starting at 1, and the acceleration is equal to 0. And here what I'm plotting is the acceleration, the velocity, and the position as a function of time. The acceleration is my input, and so I'm putting that in blue, okay? So this is my input, and I set it equal to 0 everywhere. Well, that means that the velocity has to be flat, right? Because if we go back, the velocity is equal to the original velocity plus the acceleration times time. So it has to be linear with time if the acceleration is 0, right? And so let's go to here. So the acceleration is 0, so it has to be a constant. It has to be equal to initial condition. And so the green is what I expect in both cases for the velocity and the time. And then the red is my numerical solutions. Okay, this has to work out, right? Because the acceleration is 0. And so I'm never shifting in my iterative solutions. I'm always, this is the velocity in this case, I'm always shifting, I'm grabbing the previous one and I'm shifting it times the function that I'm evaluating, which is 0. So the shift is always going to be 0. So this very simple check. This is slightly less simple, right? Because here I am solving a non-trivial differential equation. But nevertheless, it just grabs the velocity and then it just iteratively solves for the position. And so this is very similar to what we saw before. Just in this case, now the input function is just in this case it's just 1. Okay. And so the green dots is what I expect, and then the red is my solution. So they agree. Okay. So you should be able to reproduce this. A less trivial example, now I'm not setting the acceleration to 0, but instead I'm setting it to negative 9.8. Why would I do that? Any guesses? Of course, because that's the value that the gravitational acceleration takes, or the effective value of the gravitational acceleration on Earth. Okay, so the original positions and velocity, I set them both to 0 for simplicity. The acceleration I set it to negative 9.8, and so it's a constant with respect to time. And so I expect this kinematic equations to hold because I've used a constant acceleration. It's non-trivial in this case, but you see that the velocity is a straight line as it should be. So here's a solution that I expected, and this is what I obtained. So this is the green points, and the solutions are my red lines. And then same thing for the position. So here I solve just for the position as a function of time, and this is the point is what I expected, and then the red is my solutions. Good. Okay. The last check that I did is one example where I expected to not agree. So I decided to do an example where the acceleration is not constant. All right. So the acceleration grows linearly with time. So in fact, it's just equal to t. I've set the initial conditions again to be both 0 and 0. In this case, you see that now my solutions, which are the red ones, no longer agree with the solutions that I expected from the kinematic equations. And this is just to emphasize that the kinematic equations only hold if the acceleration is constant with respect to time. And so these should not agree, and they indeed don't agree. But my numerical solutions don't assume anything about the functional form of the acceleration, so I can make this acceleration to be any form. Okay, this prescription would work in general. Okay, and so this brings me to, so you have 8 exercises to cover, so you have a lot of work to do, and so I don't think I can give you any more at this point. And so this brings me to the end of today's class. And so before I answer whatever questions you have, so start bringing them in if you have any comments you may have, are always appreciated. I decided to just write down a quick summary of the concepts that we've covered. So physics concepts / equations, we talked about position, displacement, distance. We introduced concepts of speed, velocity. So we introduced velocity as a change of position with respect to time. Acceleration, which is equal to a change in velocity with respect to time. We introduced derivatives, which are the limits of rates of change. Calculus, I copied this twice. Sorry, everybody. Let me just delete that. Boop. Perfect. We introduced differential equations, and we consider linear and first order and second order differential equations, and we found numerical solutions to them. And we were able to code them up. So hopefully you're able to code them up and reproduce the figures that I've obtained. And then one concept that we introduced in Python that we hadn't used before is that you can define functions of functions, and we made use of this to make our code as general as possible. So it's a neat little trick that you might want to consider in your own code. And perhaps this is a good stopping point to see if folks have any questions or comments that we can try to address. No comments. No questions. All right. Maybe today's an early day for us. So if there's no comments or questions at this point, as always, we want to hear your thoughts. We want to hear your thoughts not just on Python for physics, but in REYES as a whole. So go to this tab and give us your feedback. Hopefully, many of you have been filling out this survey, And please do so, because we're still contemplating whether we want to continue doing REYES throughout the year, perhaps do it again next year. And so we want to figure out how to service you better and what kind of content you find most enjoyable and useful in your career. So please do so. So let me just wrap up by reminding you what we're going to be covering next time. So Tuesday, I bring it up. So Tuesday, we're going to have a talk from an introduction to quantum mechanics from Dr. Fatma Aslam, who is a theoretical nuclear physicist working at Jefferson Lab and as well as the University of Connecticut. So that's bound to be quite a bit of fun. And then next week, we're going to put into play these tricks that we've been using for solving differential equations to start modeling infectious diseases. So that's, I'm sure, going to be quite useful for you to get a better understanding of the current pandemic that we're in right now. So I would highly encourage you to stay tuned for that. So with that, let me just point you to the next session. Let me just bring up the next session that we have, which is going to start in 20 minutes. So you have quite a bit of a break. So you're welcome. And what you're going to hear is a panel from students that are going to tell you about the experience of students at ODU in the university life as a whole outside of the classroom. So you're going to be able to hear a little bit about what it's life like for those of you that are interested in perhaps coming to be students here or elsewhere. So you can hear about student organizations and the types of activities that students do outside of the classroom. I can tell you that when I went to undergrad, which was actually Alex Torso's same undergrad in the College of Florida, the life outside of the classroom was as important for me as in my education and my growth as it was the life that I experienced inside of the classroom. And so I think there's quite a bit to learn from students that are going through this experience right now. So I would highly encourage you to participate in this panel. Okay, I think we're off early today, so that's great. So everybody have a good day, and we'll see you again on Tuesday.